So far in Chapter 11, we've looked at two-period models, but of course, really in the real world, firms are competing over and over and over. And while you and I don't live forever, firms at least have the potential to live forever, right? And so we want to think about, all right, well, how long do firms need to compete in order to get some sort of, tacitly collusive agreement, right? And so first we're going to think about finitely repeated duopoly models, right? So this could be 2 periods, 3 periods, 4 periods, 5 periods, 100 periods. The problem with any finite model is that in the last period, you want to play the Nash equilibrium. So if we're thinking about a Bertrand game, you want to undercut your competitor, and we get down to the Nash equilibrium where price equals marginal cost. And so the Nash equilibrium outcome will prevail in every stage of a finitely repeated game, because you can think about every previous period as that last period of potential cooperation, right? Okay, the last period we're going to cheat. Well, if I know in the last period you're going to cheat, then I better cheat in the next to last period. And if you're going to cheat in the next to last period, then I better cheat in the period before that. And so we can't really get these collusive outcomes in a finitely repeated game. Now, that's not necessarily true in an infinitely repeated game. And so we're going to start off with an infinitely repeated Bertrand game. And the Bertrand model is nice for this because we know that the one period Nash equilibrium is where price equals marginal cost and profit is 0. And so what we're going to do is we're going to think of a trigger strategy. And so the trigger strategy is one strategy that we know we can get collusion with. It's not the only strategy. And it's not necessarily the most realistic strategy, but at least it shows that firms can get to the collusive agreement because they're able to punish each other in future periods. So the trigger strategy basically says, hey, let's set the monopoly price and we'll split the profits. And as long as you charge the monopoly price last period, then I'll charge the monopoly price next period. But as soon as you charge something less than the monopoly price, I'm going to set price equal to marginal cost and do that forever, right? And so doing that forever means that profits are going to be 0 after that. So if we're thinking about, all right, well, if I'm going to cheat or not, I have to think about what are the benefits of cheating in this current period versus cooperating forever. And so if I cooperate, then I'm going to get half the monopoly profits, right? What we're calling pi m over 2 in every period. On the other hand, if I cheat, right, I just lower my price by a penny, I get the entire market. So I'll basically get the full monopoly profit, right, minus a little bit. We'll call it pi m. But then the trigger strategy is triggered, and I'll get 0 after that. So what I want to compare is getting the monopoly profits forever, half the monopoly profits forever, versus getting all of the monopoly profits once plus 0 forever. And just remember that D here is our discount factor, right? And it's a measure of how much we value future profits. And so if D equals 1, well, that kind of explodes, but don't worry about that. Then I value future profits as much as current profits. And if D equals 0, then I don't value future profits as well. So in this case, the inequality holds as long as D is greater than 1/2, right? Which is highly likely. Now, what if there's more than one other firm, right? Well, if there's more than one other firm, then we have to share the profits between more firms, right? And so now, instead of pi m over 2 every period, I'm only getting pi m over n, where n is the number of firms in the market. And so now the inequality becomes pi m over n times 1 minus d. D is still the discount factor. Has to be greater than, cheating and getting pi m, but then getting 0 after that. And so we can solve for this inequality and see that D has to be greater than or equal to 1 minus 1 over n, or n is less than or equal to 1 over 1 minus d. And then that's just graphed here, where you can see that the discount factor needed is increasing as we increase the number of firms. But still, it's not necessarily that high, even with 10 firms, where it would be 1 minus 1 over 10 or 1 minus 0.1, it would be 0.9. And that's not an unrealistic number for a firm. Now, what about Cournot models? Well, Cournot models, they're basically the same. It's just that the algebra of the profit is a little bit more complicated, because we know that the profit in the one period game is not zero, right? It's somewhere between 0 and pi m. And so the trigger strategy is the same, right? Cooperation means the firm will produce half the monopoly output, QM over 2. And cheating means that the firm deviates by producing more than half of the monopoly output. How much? Well, they're going to choose the amount of output that maximizes their profit, given that the other firm is still cooperating and producing this QM over 2. So again, it gets a little bit more complicated, but it's really not that hard. And the trigger strategy that we need to support collusion is, all right, pi m over 2 times 1 minus d, that's the cooperation, has to be greater than whatever this profit is of cheating, plus d over 1 minus d, because that's going to be in the next period of that Nash equilibrium profit, right? That Cournot profit, which we know is still positive. And so the pi I and E that's the profit when they both produce the Cournot level, the Nash equilibrium level. And then the D over 1 minus D is the future profits that you would earn discounted by D. So the trigger strategy in the infinite Cournot game, if there is no tomorrow, then D equals 0. The inequality is not going to hold. Where pi m over 2 is larger than or equal to 1 minus d pi I star plus d times pi I Nash of the Cournot Nash equilibrium. And if d equals 1, then the inequality clearly holds. So there's going to be some value. Frankly, the graph looks very similar to what it does with the Bertrand graph. You just need a higher value of d the more firms there are, because you are sharing that monopoly profit between more of them. Now, one of the interesting things about the trigger strategy is it doesn't actually have to be forever, right? It has to be long enough, depending on the different values of D. And so what often we'll see, especially in a Bertrand type industry, is that firms will engage in price competition for a while when someone tries to cheat, and then someone will signal that the price is going back up, and they'll try to get to that collusive output again. We're seeing something similar right now with OPEC, where Russia was unwilling to agree to an output level with Saudi Arabia, and Saudi Arabia basically flooded the market and decreased the price of oil, and therefore Russians' profits as well.